Right now, a speck of dust smaller than a grain of salt is flying toward a spacecraft at 40,000 miles an hour. It hits like a hand grenade. We will follow the fleck that cracked a space station window, the grain that scarred a giant telescope's mirror, and the dust that turns into a bomb at 1/5 the speed of light. If this grips you, hit like and subscribe. Prepare yourselves. We begin. An astronaut floated up to the best window in the sky and found a wound in it. The window sits in a small dome called the cupola, bolted to the belly of the International Space Station. 7 panes of glass, 6 around the sides, 1 on top. Astronauts go there to look at Earth. They watch typhoons turn like slow white wheels. They watch cities flicker awake at night. It is the most photographed room ever built off this planet. A British astronaut drifted in one morning with his camera. He glanced at the glass, and there, sitting in the middle of one pane, was a small circular crater. A chip, about 1/4 of an inch wide, clean edges, a neat little bowl carved out of solid glass with the black of space behind it. He took a picture and sent it home. Engineers on the ground studied the shape and the depth. They worked backward. They asked one plain question. How big was the thing that did this? The answer was almost nothing. A fleck. Their best guess was a chip of paint, peeled off some old rocket body years earlier and left drifting in orbit. The estimate came out to a few thousandths of a millimetre across. Smaller than a grain of salt, smaller than a grain of flour, smaller than the period at the end of a sentence in a paperback book. Drop it on your fingertip and you would feel nothing. Look for it and you would see nothing. That is what carved the crater. The cupola glass has 4 layers, and every layer has a job. The outermost pane is called the debris pane. Its entire purpose in life is to be ruined. It stands there and takes the hit so the layers underneath survive. Beneath it sit 2 thick pressure panes, and those are the ones that hold back the vacuum. Those are the ones keeping the air inside the room, and the astronaut inside his own skin. On the outside there are metal shutters that swing closed whenever nobody is using the view, so the system worked exactly the way it was drawn on paper. The fleck died on the sacrificial layer. Everyone was fine. Here is the part that keeps engineers awake. The station gets hit like this constantly, every single day. When astronauts photograph the outside of the station in detail, they find scars everywhere. Pits in the handrails they grab during spacewalks, freckles across the radiators, dimples in the aluminum skin. It looks like the surface has a case of metal acne. Every one of those marks is a separate collision with something too small to track and too fast to dodge. The arithmetic feels wrong. A speck of dust should bounce. It should skitter off like a crumb flicked across a table. It has the mass of a shadow. It should leave a smudge you could wipe away with a thumb. Instead, it dug a pit into glass built to survive an orbital lifetime. The answer lives entirely inside one number. Forget the size of the fleck. Forget what it was made of. Forget where it came from. That number is speed. And once you understand what speed does to a grain of dust, the entire idea of building a starship starts to look very different. Put a bowling ball on a table and roll it toward your hand. It taps you. Now imagine that same ball dropped from a plane. Same ball, same mass, completely different day, same ball, same weight. The speed changed everything, and in a collision, speed multiplies the damage, then turns around and multiplies it again. The energy inside a moving object depends on how heavy it is and how fast it goes, but those 2 ingredients are treated very differently. Double the mass and you double the energy. Double the speed and you get 4 times the energy. Triple the speed and you get 9 times. Speed gets squared. Mass just sits there. This is why a paint fleck beats a hammer in space. Sit still and imagine a rifle. A bullet leaves the barrel at roughly 2,000 miles an hour. Fast enough to punch through a door. Fast enough to end a life. Fast enough that your eye will never see it leave. Now look at low Earth orbit. Everything up there is racing around the planet at about 17,000 miles an hour. That is orbital speed. It is the price of not falling down. And if 2 objects are circling in different directions, they do not meet at 17,000. They meet at the sum of both. Head-on collisions in orbit happen at more than 30,000 miles an hour. That is 15 rifle bullets stacked into one impact. And the natural dust is worse. Grains shed by comets are not orbiting Earth at all. They are orbiting the Sun on wild, tilted paths, and they cut across our neighbourhood like traffic running a red light. Those grains can arrive at more than 160,000 miles an hour. New York to Los Angeles in under 1 minute. Now put a number on it. Take a single fleck of aluminum weighing 1 gram. That is about the weight of a paperclip. Give it the speed of a typical orbital collision. Run the energy math. The paperclip carries the same punch as a bowling ball slammed into you at 260 miles an hour. 1 paperclip, delivered like a car crash on a racetrack. Shrink the fleck down 1,000 times to something you cannot see, and the energy drops with it. But it does not vanish. It becomes the energy of a heavy hammer swung hard by an angry adult, focused onto a spot narrower than a human hair. All that force squeezed into a pinprick. That is why the crater in the cupola window has such clean edges. The fleck concentrated a hammer blow into a single dot, and the glass gave way underneath it. Engineers gave this whole regime a name. They call it hypervelocity. The definition is simple. It is any impact fast enough that the strength of the material stops mattering. Hold on to that sentence. The strength of the material stops mattering. Steel, aluminum, glass, bone, titanium. Above a certain speed, the difference between them shrinks to almost nothing. Being tough is a strategy that only works at slow speeds. Up there, toughness runs out of relevance. So what actually happens when a grain of dust arrives at 40,000 miles an hour and hits a wall of solid metal? Something that looks nothing like a collision. Something that looks like a splash. Slow the clock down, way down. Take 1 impact and stretch it out until you can watch it happen. A grain of dust closes on an aluminum plate. In the last instant before contact, everything is normal. Solid grain, solid plate. 2 ordinary objects about to meet. Then they touch, and physics loses its manners. The grain cannot push the plate out of the way, because there is no time. Metal moves out of the way at the speed of sound inside metal, roughly 10,000 miles an hour. The grain is arriving 3 or 4 times faster than that. So the plate cannot get the message. The atoms at the impact point have no warning and nowhere to go. The pressure spikes to something absurd. Millions of times the pressure of the air around you, higher than the pressure at the bottom of the deepest ocean trench by a huge margin. Under that kind of squeeze, aluminum stops behaving like a table and starts behaving like a puddle. Think of a raindrop landing in a pond. It splashes. A crown of droplets leaps up and out, and a bowl-shaped dent opens in the surface before it heals over. That is the picture. At these speeds, solid metal flows exactly like that pond. The grain digs in, and a shock wave races ahead of it into the plate. A second shock wave races backward into the grain itself. Both objects get crushed and heated at the same instant. The temperature at the contact point climbs past the melting point of the metal, then past the boiling point, in less time than it takes a nerve signal to leave your fingertip. The grain vaporizes. It turns into a puff of glowing gas, in the time it takes light to cross a small room. And so does a chunk of the plate. Some of that gas gets hot enough to strip its own electrons off, which turns it into plasma, the same state of matter that fills the sun. For roughly 1/1,000,000th of a second, a tiny piece of the sun exists on the hull of a spacecraft, then it's gone. The metal splashes outward, a crown of liquid aluminum blooming up and away from the hole. It freezes almost instantly in the cold, locking that splash in place forever. Look at real impact craters under a microscope and you can see it. A frozen ripple, a wave caught mid-crash, the bowl shape from the raindrop analogy, stamped permanently into the wall. Here is the number that should bother you. The crater is far bigger than the grain that made it. A speck can carve a hole 10 times its own width, sometimes more. The dust excavates, and a fresh problem gets born in that instant. The blast throws a shower of metal fragments off the far side of the plate, out of the back into the room beyond. The plate never got punctured, the dust never made it through, but the wall itself becomes shrapnel and sprays the interior anyway. The wall turns into the weapon, which raises an obvious question. If a grain of dust does all this, how did anyone ever test it on the ground? You cannot buy a gun that shoots at 40,000 miles an hour, so scientists had to build one, and even their best machine falls short. There is a building in the New Mexico desert where people fire a gun the size of a school bus at a scrap of foil and then spend a week studying the hole. The gun exists because of a problem. To design armor for spacecraft, you have to hit things at spacecraft speeds. Nothing on Earth naturally moves that fast. A rifle tops out around 2,000 miles an hour. A tank round, the fastest gun on any battlefield, reaches maybe 4,000. Both are pitiful compared to what a grain of dust does casually every day above your head. So engineers cheated. The machine is called a two-stage light gas gun, and it works in a chain reaction. Stage 1 is a normal charge of gunpowder. It fires a heavy plastic piston down a wide barrel. That piston slams into a tube packed with hydrogen gas and squeezes it, hard. The hydrogen has nowhere to run. Its pressure explodes upward. Its temperature climbs to thousands of degrees. Hydrogen is chosen because it is the lightest gas in the universe, and light gas can move fast. Heavy gas is sluggish. Hydrogen atoms are already whipping around at enormous speed, so when you squeeze them they push back with terrifying eagerness. A thin metal disc holds the pressure until it cannot. It bursts. All that furious hydrogen rushes into a narrow launch tube, and it grabs a small sphere sitting there, sometimes plastic, sometimes aluminum, often no bigger than a bead of rice. The bead comes out at about 18,000 miles an hour. That is a rifle bullet times 9. The whole building shakes. The gun weighs many tons and it recoils anyway. And a millisecond later the bead is a memory, splashed across a target plate. High-speed cameras catch the moment. What comes back is a glowing cloud, an expanding flower of vapor and liquid metal, blooming out of the target like a firework opening in the dark. Now here is the frustrating part. 18,000 miles an hour is the best that machine can do, and real micrometeoroids arrive nearly 10 times faster. The gun that took decades to perfect, that needs a desert and a bunker and a team of specialists, still cannot reach the speed of an ordinary grain of comet dust falling through the solar system. So the science hits a wall. Engineers fire what they can, measure the craters, and then feed those results into computer models that extrapolate the rest. They are guessing the top of the graph from the bottom of it. Every shield on every spacecraft you have ever heard of was designed partly on a curve that stretches beyond anything anyone has tested. Every one of those curves has a point where the measurements stop and the faith begins. Some teams push harder. They use exploding wires to accelerate flyer plates. They use particle accelerators to hurl single-charged dust grains at speeds that finally rival the real thing. But only one grain at a time, and only for grains 1,000 times smaller than the ones that scare them. Nature, meanwhile, runs this experiment at full power, for free, everywhere, forever. And once a year, Earth flies straight into the middle of it, straight into the ashes of a dead comet. Satellite operators mark the date on the calendar, and some of them hold their breath. Every August, people spread blankets on grass and look up to watch the Perseid meteor shower, and almost nobody realizes they are watching a bombardment from below. Those streaks are dust. Ordinary comet grit, most of it the size of a sand crystal, burning up 60 miles overhead. The comet that made them is a mountain of ice and rock that swings past the sun every 130 years. Each pass, sunlight boils its surface and blows off a haze of dust. That haze lingers. It stretches along the comet's orbit like smoke from a slow train, and it sits there for centuries. Earth crosses that smoke trail once a year, at the same time, on schedule, forever. Down here you get a light show. Up there, you get a shooting gallery. Now go back to the summer of 1993. The comet had recently swung through, and the trail was fresh and thick. Astronomers warned that this year's crossing would be unusually heavy. Satellite operators listened, and many of them took precautions. Some turned their spacecraft to present the smallest possible profile, edge onto the stream, like a man turning sideways in a crowd. One satellite belonged to Europe. It was a large communications platform, a workhorse, the biggest civilian satellite Europe had ever flown at that point. It had already survived years in orbit. During the peak of the shower, it started to go wrong. Something struck it. The strike appears to have generated an electrical discharge, a sudden burst of charge that scrambled the electronics. The satellite lost its grip on its own orientation. It began to drift, then to tumble. Controllers on the ground fought to recover it. They burned fuel trying to stabilize it and point it home. They got it back under control. And in doing so, they used up nearly everything it had left in the tank. Weeks later, the mission was declared over. A satellite that cost hundreds of millions was retired because of a piece of comet. The grain that likely did it would have been a fraction of a millimeter wide. You could have lost it in a sugar bowl. Here is the mechanism that makes comet dust extra nasty. It arrives at insane speed, so it vaporizes into plasma, and plasma conducts electricity. A satellite floating in space carries a static charge, the same way you do when you shuffle across a carpet. Dump a little cloud of conductive plasma onto that charged surface, and the stored charge finds a path. It jumps. The spark does the killing, and the dust just opens the door. So the danger doubles. The impact can wreck the metal, and the flash can wreck the brain. A few years later, another shower arrived, this one seeded by a different comet, and the forecast was worse. Operators around the world prepared like a hurricane was coming. Some spacecraft were rotated, some instruments were switched off entirely, on the theory that a dead circuit cannot be shorted out. The storm passed. The fleet mostly survived. But nobody wants a strategy that consists of turning everything off and hoping. The real answer came from a mind that had already spent a lifetime thinking about comet dust. A man who figured out what comets were made of decades before any spacecraft ever visited one. His fix sounds like a mistake. He said the way to stop a bullet is to make the wall thinner. 1946. No satellites. No space program. Nobody had put anything into orbit, and the idea was still filed under fantasy by most serious people. One American astronomer sat down and did the math anyway. He studied comets. He was the one who worked out that a comet is a dirty snowball, a lump of ice with rock and dust frozen inside, shedding grit every time it warms. He knew better than almost anyone alive how much junk floats through the solar system and how fast that junk travels. So he asked the question nobody needed answered yet. If we ever build a ship for that environment, what kills it? His conclusion was that dust kills it, and then he proposed a fix so strange that it took years for people to believe him. The obvious plan is armor. Make the wall thick. That is how humans have solved incoming objects since the invention of the shield. Castles have thick walls. Tanks have thick walls. Bank vaults have thick walls. More metal, more safety. It is one of the oldest instincts we have. He said no. He said a thick wall is the worst possible choice because weight is the enemy in space, and because a thick wall handles hypervelocity impacts badly anyway. The grain drills straight in, and all its energy goes into one spot, and one spot is exactly where you least want energy. His idea was this: put a thin sheet of metal out in front of the hull, not touching. Hold it a few inches away on standoffs, with nothing but empty space in the gap. Make the sheet almost flimsy. Make it thin enough to tear like a can lid. Then let the dust hit that. The bumper, he called it. And the logic is beautiful. The dust wants to stay a solid object. A solid object is dangerous because it holds all its energy in one hard little package. So you let it in, and you destroy it on the way through. You force it to stop being an object. The thin sheet does that. The grain goes through it easily, and the sheet does not care about stopping the grain. In the act of punching through, the impact shock rips through both the grain and the sheet metal at once. The pressure spike is enormous, exactly like we saw in the crater. The grain shatters, melts, and boils away. The sheet does the same locally. What comes out the backside is a cloud. The bumper is a trap wearing the costume of armor. Its job is to be pierced. It converts one concentrated threat into a spray of harmless fragments, and it uses the enemy's own speed to do it. The faster the dust comes in, the better the bumper works because faster impacts vaporize more completely. That is the part that flips your brain around. Slow dust would survive the bumper as a solid chunk. Fast dust destroys itself on it. This is the closest thing to judo that engineering has ever produced. The design is still used on almost every serious spacecraft flying today. Look at photos of the station's exterior and you're mostly looking at bumpers. But we skipped the important part. The bumper does not do the saving. The gap does. And what happens in that gap, in the few inches of nothing behind the sheet, is where the real defense lives. A grain of dust dies at the front sheet. Then it gets 3 or 4 inches of empty space to think about what it has done. That empty gap is doing the actual work, and once you see why, the whole design snaps into focus. Picture the moment right after the bumper is pierced. The grain has been vaporized. Part of the sheet has been vaporized. What crosses into the gap is a mixture of gas, plasma, molten droplets, and tiny solid splinters, all of it still carrying most of the original speed. And that mixture is expanding. It leaves the hole in the shape of a cone, spreading sideways as fast as it moves forward. The little cloud swells like a puff of breath on a cold morning, growing wider every microsecond it travels. Engineers call it the debris cloud. It looks, in high-speed footage, like a jellyfish made of a light. By the time it crosses those few inches of gap and reaches the real hull, that cloud has spread across an area vastly larger than the original grain. What arrived as a pinprick now arrives as a wide, soft slap. Same energy, same speed, spread over 100 times more surface. Take a heavyweight boxer and let him punch you with a bare knuckle, then let him swing exactly as hard, with exactly the same muscle, into a wide, flat pillow strapped across your chest. Identical energy, both times. One of those breaks a rib, the other knocks the wind out of you. Pressure is force divided by area. That is the whole secret. You cannot delete the force. You can absolutely change the area. So the inner hull, which is thicker, takes a broad, diffuse push instead of a needle. It dents, it bulges, it gets peppered with a fine spray of pits, it stays sealed. Make the gap wider, and the cloud spreads more, which means the protection improves without adding a single ounce of metal. Empty space is the lightest armor ever invented, and it costs nothing to launch. Now, the grim details. This trick has a ceiling. Send a bigger grain, and it does not fully vaporize on the bumper. It punches through and keeps a solid core surrounded by a halo of debris. That surviving core is still a bullet, and now it has a shotgun blast escorting it. Send something bigger still, and the bumper is barely an inconvenience. It is aluminum foil. The object continues, essentially unbothered, into the hull, through the hull, and out the other side of the spacecraft. There is also a nasty middle ground. Certain impact speeds are worse than faster ones. Too slow, and the grain refuses to vaporize properly. It arrives at the rear wall as a lump. Engineers have to design for the worst case in that window, rather than the fastest case. And a 2-sheet shield weighs less than a solid wall, but it still weighs something. The station is enormous. Wrapping every surface in bumpers and gaps would add tons of mass, and every ton costs a fortune to lift. So the pure design gets ugly fast. Real shields on real spacecraft are stranger than 2 sheets of aluminum. They have ceramic cloth in them. They have bulletproof vest material in them. They have layers that were originally invented to stop pistols on a street corner. The armor around sleeping astronauts is stranger than you think. Slice open the wall of the module where astronauts sleep, and you will find something you could buy at a police supply store. The basic 2-sheet design has a weakness. The debris cloud spreads, yes, but it still carries splinters, and splinters can be sharp and stubborn. So engineers asked a follow-up question. What if we put something in the gap? Something light. Something that eats fragments. The first ingredient is a ceramic cloth. It is woven from fibers of aluminum oxide and boron and silicon, and it looks like a stiff white bedsheet. It is the same family of material used to insulate furnaces. It handles heat that would turn aluminum into soup, and more importantly, it is a nightmare for a hypervelocity fragment. The fragment hits a fiber, breaks apart on it, gets slowed and scattered, then hits another fiber and another. The cloth is mostly empty space, so it is feather-light, and each layer strips a little more menace out of the cloud. The second ingredient is the bulletproof one. It is the same aramid fiber used in police vests. In a vest, its trick is catching a bullet in a net of incredibly strong threads and spreading the punch across your chest. In a spacecraft wall, it does exactly that job for whatever survived the ceramic. Stack it all up. Thin aluminum bumper on the outside. Gap. Layers of ceramic cloth. Layers of aramid fabric. Gap. Then the real pressure wall. The aluminum that holds the air in. Engineers name this the stuffed shield, which is the least dramatic name for the best armor humans have ever built. The numbers are worth sitting with. A bare aluminum wall might stop something a fraction of a millimetre wide. The stuffed shield on the station stops objects up to about half an inch across. That is a marble, travelling at 30,000 miles an hour, stopped by 2 thin sheets, a blanket, and a vest. To match that performance with a single slab of solid metal, you would need a wall so thick that no rocket ever built could lift the station into orbit. And the station wears this armour like a patchwork quilt. There are well over 100 distinct shield designs bolted to that structure, tailored surface by surface. The Russian modules use their own approach. The American laboratory uses another. Certain faces get heavy protection. Certain faces get almost none. Why the difference? Because the threat is not the same in every direction. The station flies through orbit like a car on a highway, and it has a windshield side and a back bumper side. The forward-facing surfaces plough into everything. They collect impacts at combined speed. The trailing surfaces are running away from most of it, so debris has to catch up, which means slow, weak hits. There is also an up and a down. Below is Earth, which shields a big slice of the sky. Above is everything else, so the armour gets distributed like money in a tight budget. Thick where the risk lives, thin where it does not, and in a few places nothing at all, which means someone somewhere sat in a room and drew a line on a diagram of a place where humans live, and decided that this section was worth protecting, and that section was worth the gamble. That decision is made with a number, and the number is a probability. Every crewed spacecraft flying today is protected by a calculation with a polite name and a brutal meaning. The name is probability of no penetration. It answers one question. Over the life of this mission, what are the odds that nothing punches a hole in it? Notice what that question admits. The odds are never 100%. They never can be. Somewhere in the design documents for every station and capsule ever flown, there is a number that quietly says, here is the chance we lose. Engineers run this with a computer model that chews through the whole structure. It knows the shape of every module. It knows which way each surface faces. It knows how the station rotates and how it flies. It carries a map of the dust and debris environment, built from decades of measurements, and it fires simulated particles at the whole vehicle from every direction millions of times over and counts the failures. Then the design gets pushed around until the number is acceptable, and acceptable is a human choice. A committee decides how much risk a crew is allowed to carry. There is no natural law that hands you that number. People argue it out in meetings. Mass is what forces the argument. Armour is heavy, launch is expensive, and every pound of shielding is a pound of science, food, water, or fuel you leave on the ground. So protection is rationed like water in a desert. The result is a station with soft spots. Everybody knows where they are. There are charts. Which leads to one of the strangest procedures in human spaceflight. When ground controllers spot a piece of debris that might come close, and they cannot move the station out of the way in time, they wake the crew and tell them to go sit in their return capsules, hatches closed, strapped in, waiting. The logic is cold and sensible. If a module gets holed and starts venting air, the crew is already sitting in the vehicle that takes them home, and they can undock and leave. It has happened more than once. Crews have spent hours floating inside their lifeboats, listening to nothing, waiting for a scheduled moment to pass, wondering if they will feel it. They never feel anything. The debris misses, the clock runs out, and they go back to work and eat breakfast. Sit with the picture. Astronauts sealed in an escape pod, hiding from an object they cannot see, that they cannot dodge. That is probably harmless. That might kill everyone. Then a shrug, and back to the treadmill. But that whole system, the model, the odds, the shields, all of it rests on one shaky foundation. The map of the environment. You cannot calculate the risk from dust unless you know how much dust is out there, how big the grains are, how fast they come, and where they come from. And in the beginning, nobody knew any of that. Not really. There were guesses drawn from meteor counts and telescope work, and the guesses disagreed with each other wildly. So somebody proposed an experiment with a beautifully stupid premise. Build a satellite whose only purpose is to get shot at. Leave it in orbit. Bring it home. Count the wounds. They did it. And then the plan went horribly wrong in a way nobody wanted, and it turned into the best dust experiment ever run. The plan was simple. Put a bus-sized cylinder in orbit, cover it in experiments, leave it there for about a year, then go back with a space shuttle and carry it home. The satellite had no engines, no steering, no way to point itself. It was a giant 12-sided drum, roughly 30 feet long, covered in trays like a tackle box, and it was designed to do nothing at all except hang there and get hit. It went up in 1984. The shuttle placed it in orbit, and it settled into a stable attitude, with one face always leading and one face always trailing. That detail turned out to matter enormously. Retrieval was scheduled for about a year later. Then Challenger was lost, and the entire shuttle fleet stopped flying. The program went into a long, painful rebuild. Missions were cancelled and reshuffled. The little drum of experiments way down the priority list kept circling, alone, unpowered, unwatched. 1 year became 2, 2 became 4, 4 became 5. Meanwhile, its orbit was slowly decaying. Even at that altitude, there are traces of atmosphere, and traces are enough. It was falling, slowly, then less slowly. Engineers worked out that it had about a month of life left before it burned up and took its data with it. A shuttle crew got to it with weeks to spare. They found something extraordinary. Almost 6 years of continuous exposure on a surface nobody had touched in a known orientation, with every single surface catalogued before launch. It was the cleanest experiment imaginable, created entirely by accident. They flew it home and scientists swarmed it. The count came back in the tens of thousands, more than 30,000 visible impact craters across the outside. The biggest was about 1/4 of an inch wide. The smallest needed a microscope. Every one of them was a separate high-speed collision with something invisible, and because the drum never spun, the pattern told a story that no other experiment could tell. The leading face was hammered. The trailing face was nearly clean. The ratio between them, front to back, was enormous. That asymmetry proved something crucial. A large share of the impacts came from objects orbiting Earth in the same direction, catching the satellite from the front. Human garbage. Then the chemistry finished the argument. Scientists scraped the residue out of individual craters and analysed it under an electron microscope. Some craters held traces of stone and carbon, chemistry that matched comet dust and asteroid chips. Nature. Other craters held aluminum, titanium, and flakes of paint. Every fleck of paint was a message from us. That is the moment the debris problem stopped being theoretical. Before the drum, the argument over how much junk we had left up there was an argument about models. After it, we had physical samples of our own trash, embedded in craters, sitting on a table in a lab in Virginia. This accidental masterpiece became the foundation for every debris model that came afterward. The station's shields exist because a shuttle disaster stranded a passive experiment for 5 extra years. But 6 years is a snapshot. To see whether the danger is growing, you need to go back and look again, later. You need the same surfaces, exposed twice, decades apart. There was exactly one machine in orbit that could give us that, and astronauts had already been sent to repair it. Hubble was born with a flaw in its eye, and the rescue mission that fixed it accidentally handed scientists a time machine for dust. The telescope had 2 enormous solar wings, delicate blankets of cells rolled out on either side of the tube. They were exposed to open space, flat, wide, and utterly undefended. Then astronauts flew up to fix the famous mirror problem, and while they were there, they replaced those wings. And they brought the old ones home. 3.5 years of exposure came back to Earth in a cargo bay, and researchers went over them with microscopes. Thousands of craters, small ones, medium ones, one hole big enough to see from across a room. A decade later, another crew went back and swapped the wings again. Those had been up for more than 8 years. Home they came too. Now scientists had the same object, made of the same material, in the same orbit, exposed across 2 different time periods. That is a control group in space. Nothing else like it has ever existed. They counted, they measured, they compared. The picture that came out was a portrait of an environment getting busier, and the chemistry inside the craters told them who was responsible for what. Natural grains from comets tend to be dark, carbon-rich, and fragile. Human debris leaves aluminum oxide, paint, and metal. Here is a detail that sounds like fiction. Some craters contained residue from solid rocket motors. When a rocket burns solid fuel, it throws out a fine exhaust of aluminum oxide particles, tiny glassy spheres, sometimes only a few thousandths of an inch across, millions of them. Every solid rocket launch sprays a cloud of microscopic glass beads into space, and those beads stay up there and orbit. Scientists found them, welded into the wounds of a telescope, a decade after somebody lit a candle in Florida. Even the smoke from our engines becomes ammunition. The wings also revealed something about scale. The craters formed a slope. For every big crater you find many more medium ones. For every medium, you find a swarm of small ones. Shrink the size, multiply the count. The environment is a pyramid, and the base of that pyramid is enormous, which sounds reassuring since small hits do less harm. The comfort dies fast. It means the sky's thick with objects at exactly the size that no one can see, no one can track, and no one can dodge. The wings carried a second kind of scar as well. Whole patches had lost their coating, eaten away by atomic oxygen, the shredded remains of Earth's air still clinging to that altitude. Dust punches, oxygen corrodes. The two work as a team, because every fresh crater peels back the surface and hands the oxygen a new place to chew. So we have a telescope pockmarked like an old stop sign, and a station wearing a coat of bumpers, and none of it has hurt anybody yet. Because so far, every hit we have talked about has been small. Small enough to die on a sacrificial layer, small enough to leave a scar and a story. Time to ask the question the engineers ask each other quietly. What happens if one of these things is the size of a marble and it hits the wall of a module with people inside? A half-inch sphere of aluminum moving at orbital speed carries about the same energy as a small car on a highway. That is the honest comparison. Something you could hide in your fist delivering the energy of a sedan at 50 miles an hour focused into a spot the width of a coin. The station's best shielding is designed to stop roughly that, which means it sits precisely at the edge. A little smaller, and the shield wins. A little bigger, and the shield becomes decoration. So run the failure. A marble arrives at a lightly protected section. The bumper does its job and dies. The debris cloud forms, but it is fat and violent this time, and it still carries a surviving solid core. The ceramic cloth chews on it. The aramid layers catch what they can, and then the whole ugly mess arrives at the pressure wall, and the pressure wall loses. The moment the hull opens, the room changes into something with weather. Air rushes for the hole at the speed of sound. The pressure inside drops. Loose objects sail toward the breach, and anything small enough gets sucked into it and jams there, which sounds lucky. Alarms scream. The temperature falls, moisture in the air condenses instantly, and a fog fills the module. How long the crew is depends entirely on hole size. A small puncture, 1/4 of an inch, gives them hours. That is a survivable day. They find it, they patch it, they carry on and tell the story at dinner for the rest of their lives. A hole a few inches wide gives them minutes. There is a smaller nightmare that does not require a hole at all: spalling. The impact can hurt you straight through a sealed wall. It shocks the metal so violently that the inside face shatters off on its own and sprays the room with fragments at rifle speed. The hull stays sealed, the crew does not, and the worst version is the one nobody can plan for. It hits something that matters. A power line, a cooling loop full of ammonia, a tank of pressurized gas which turns into a bomb when something punctures it at that speed, and then the fragments from that tank hit everything else nearby. The response plan is real, rehearsed, and practiced constantly. Astronauts train to hunt a leak by listening, by watching a floating scrap of tape drift toward the airflow, by using ultrasonic detectors that hear the hiss you cannot. They train to seal hatches and abandon a module, sacrificing an entire room to save the rest. They keep patch kits with sticky plates and foam, and if the leak wins, they get in the capsule and go. Now the good news, and it comes with a knife in it. A marble-sized object cannot be seen from the ground. The tracking network watches things about 4 inches across and larger. Below that, the sky's a fog, which means the marble that could vent a module is invisible to us right up until the moment it arrives. There is no warning system, there is no alarm, there is only armour and odds, except in one place. There is one part of the station where the wall is transparent, and glass cannot be stuffed with ceramic blankets or wrapped in a bulletproof vest. which is why the best view in the solar system is protected by a piece of engineering designed to be destroyed. A window is a hole in your armour that you cut on purpose. Every other surface on the station can be layered, stuffed, blanketed and hidden. The cupola cannot. Its whole reason for existing is to let light through, and light will not travel through Kevlar. So engineers did something clever. They gave up on the idea of a window that survives and built a window that heals. 4 panes. Start on the outside. The first is the debris pane. It carries no load. It holds back no air. Its life plan is destruction. It is there so that a fleck of paint will find something to hit that nobody needs. It gets chipped, scarred, and slowly frosted with tiny craters, and every one of those scars means the layers below stayed clean. Behind it sit 2 thick pressure panes made of fused silica, and they are the real wall. Either one alone can hold the station's atmosphere against the vacuum. There are 2 of them because engineers refuse to bet a life on a single sheet of anything. Then, on the inside, a scratch pane. That one exists to protect the expensive glass from the greatest hazard of all: astronauts. Elbows, cameras, tools, and the daily traffic of human beings living in a small metal room. The system has a 5th layer, and it is the strangest. Every window has an aluminum shutter that closes over it from the outside, controlled by a crank inside. When nobody is looking through the glass, the shutter is shut. The default state of the best window ever built is blind. Think about the implication. The station keeps its eyes closed unless someone is using them, because open eyes get hurt. Astronauts crank the shutters back to take a photograph, then crank them closed again. The view is rationed like ammunition, and still, the glass collects wounds. Impact damage on station windows is monitored, measured, catalogued, and tracked over time. Windows on earlier spacecraft had to be replaced after single flights, because a fleck went too deep. The shuttle came home with chipped windshields on multiple missions. One chip was traced to a flake of paint. Crews photograph the panes on a schedule and beam the images down, and analysts measure every new pit and log it in a database that has been quietly growing for decades. Now, the honest limit, this design works for specs, nothing more. A window survives dust and paint. A window loses to a pebble, immediately and completely, and no amount of layering changes that. Glass is glass. So the entire strategy for the transparent parts of a spacecraft comes down to accepting damage, keeping the shutters closed, and hoping the big one goes past. That works for a station where astronauts can crank a lid over the glass and go read a book. It falls apart the moment your spacecraft is unmanned. Alone, millions of miles from anyone, and covered in enormous, thin, delicate surfaces that must stay open to the sky to work at all. Solar panels have no shutters, antennas have no shutters, mirrors have no shutters. And a few years ago, a European satellite was flying quietly along, doing its job, when its own cameras caught the exact moment a grain of dust hit its wing. The picture that came back changed what engineers thought a small particle could do. The satellite noticed the hit before anyone on Earth did. It was a radar satellite, a European workhorse, part of a fleet that maps the planet through cloud and darkness. It watches ice sheets crack. It spots oil spills. It measures how the ground moves after an earthquake, down to fractions of an inch. It is one of those quiet machines that most people have never heard of and everyone benefits from. One afternoon in the summer of 2016, ground controllers saw 3 things happen at once: a small drop in power, a tiny change in the satellite's orientation, and a nudge to its orbit. The last one is what made everyone sit up. Something hit it hard enough to push the whole spacecraft. Now this satellite had cameras. They were there for a boring reason: to watch the solar arrays unfold after launch and confirm they had deployed properly. That job was finished years earlier. The cameras were basically a leftover. Engineers switched them on and looked. There was a gouge in the solar wing, roughly 16 inches across, on a panel, in a picture, taken by the victim. Then they worked backward, the way they did with the window chip. Crater size gives you a bound on the attacker. The answer came out at somewhere under a millimetre, possibly a few thousandths of an inch. A speck of grit smaller than a poppy seed tore a hole the size of a dinner plate and shoved a spacecraft weighing more than a ton off its path. That is the moment the whole story escalates. Because a solar array is a thin, wide, brittle sheet. It has no bumper, no gap, no ceramic blanket. It cannot have any of those things, because it has to catch sunlight and armor block sunlight. The design forbids the defense, so panels take hits raw. Every satellite in orbit is flying with 2 enormous unarmored wings, and those wings are usually the biggest part of the vehicle. The satellite survived. It lost a slice of power and kept working, because engineers build panels with redundant strings of cells, and losing one section is a wound rather than a death. They compensated, adjusted, and the mission carried on. Nobody will ever repair that wing. There are no mechanics in orbit, and the wound stays open for the life of the machine. But the lesson was ugly. There was nothing special about the particle. It was routine. It was the kind of thing that hits spacecraft every day. The only unusual part was that a camera happened to be pointing at the wound, which raises a horrible question. How many satellites have taken hits like this that we never saw? How many mysterious power drops, tiny attitude wobbles, and unexplained glitches over the last 50 years were actually a grain of dust and got written up as an anomaly and forgotten? Nobody knows. Most spacecraft cannot look at themselves. They have no mirrors, no cameras, no way to check their own skin. They just report symptoms, and if a poppy seed can do that to a solar panel, then a question follows that nobody in astronomy wanted to ask out loud. What happens when one hits the most valuable mirror ever launched, made of gold, unfolded 1 million miles from any human being, with no possibility of repair ever? We did not have to wonder for long. 6 months after launch, the newest great telescope was still being tuned, and something struck it. The mirror is the heart of the machine. 18 hexagonal segments of beryllium, coated in a whisper of gold, arranged into one enormous honeycomb over 20 feet wide. It sits 1 million miles from Earth, 4 times farther than the Moon, in a spot where no astronaut can ever reach it. There will be no repair mission. Whatever happens to that mirror is permanent, and it flies naked. There is no lid, no dome, no shutter. A telescope with a closed eye is a paperweight. Engineers knew dust would hit it. They planned for it. They had run the models, and they expected small strikes to accumulate slowly over the years, degrading the mirror by a fraction of a percent, the way weather ages a car. In the first half year, the telescope logged several small strikes, and every one of them behaved exactly the way the models promised. Then, in May of 2022, one of the segments took a hit that was bigger than anything in the plan. The damage showed up in the data as a permanent change in the shape of that segment. Engineers can adjust each mirror piece with tiny motors, nudging them with astonishing precision to keep the whole honeycomb working as one perfect surface. They used those motors to compensate as much as they could. They got most of it back. A trace of the damage stayed, and it will stay for as long as the telescope exists. The telescope still works beautifully. Its images are the sharpest infrared pictures anyone has ever taken, but a permanent mark now lives in the mirror, and the team had to sit down and rethink their assumptions. Their conclusion was blunt. This grain was probably an unlucky draw from the natural population, a rare, larger particle arriving early, or possibly a sign that the models underestimate how many big grains are out there. Both possibilities are unpleasant, so they changed how they fly. The telescope now avoids pointing into its own direction of travel whenever possible. Look forward, and you meet dust head-on, at combined speed, exactly like a windshield in rain. Look sideways or backward, and dust must chase you down, which weakens every impact. They named the forbidden direction the micrometeoroid avoidance zone. Astronomers now schedule observations around it. Somewhere on Earth, someone with a doctorate spends part of their week arranging the study of the early universe around the traffic pattern of dust. Sit with the scale of that for a second. A machine that cost billions, built by thousands of people over decades, carrying the hopes of an entire science, and its operating manual now includes a rule about which way to face so it does not get sandblasted. The mirror will keep getting hit. Every year it collects more. There is a slow clock running on that gold surface, and every tick is a grain. So the obvious solution is to see them coming and move. We track debris around Earth. We move the station out of the way when we need to. Why not just watch for the dangerous ones? The answer explains everything else in this story. We cannot see them, not most of them, not even close. There is a global network of radars and telescopes staring at orbital space, day and night, and it is functionally blind to everything that actually hits us. The network is impressive. Powerful radars sweep the sky and paint returns off passing metal. Optical telescopes catch sunlight glinting off objects higher up. Computers stitch it together and maintain a catalogue of tens of thousands of tracked objects, updated constantly. Every dead satellite, every spent rocket stage, every discarded bolt big enough to register. When something in that catalogue is heading near the station, controllers get a warning. They calculate a box around the station, roughly a mile deep and a few dozen miles wide. If the intruder is going to enter that box with any real probability, they fire the thrusters and move a 400-ton structure out of the way. This has been done dozens of times. The system works, and it has a flaw. In low orbit, the network reliably tracks objects about 4 inches across and bigger. Below that size, things get patchy. Below an inch, they are essentially invisible. Now count what lies underneath that flaw. Objects bigger than 4 inches, the ones we can see and dodge. Tens of thousands. Objects bigger than about half an inch, the marble that beats our best armour. Hundreds of thousands. Objects bigger than a millimetre, the poppy seed that tore that solar wing open. More than 100 million. 100 million. And that is only the human-made junk. It does not include the natural comet dust falling through the whole solar system forever. So the catalogue we track is the tip of a mountain, and the mountain has no bottom. The reason for the blindness is physics. Radar works by bouncing a signal off a target, and the returning echo gets weaker at a savage rate. Double the distance to the object and the echo drops by a factor of 16. Shrink the object and the echo collapses too. A 1mm fragment at 400 miles, tumbling and dark, returns an echo so faint it drowns in the noise of the atmosphere. You cannot fix this by trying harder. You could build a radar the size of a city and still lose the grain. That is the shape of the problem. Every threat splits into 2 bins. Big enough to see, which means we dodge it, which means it never hurts us. Too small to see, which means we cannot dodge it, which means we take it on the shield and pray. There is no third option. There is no early warning for dust. There never will be. So the strategy for the entire human presence in space rests on armour and statistics. Build the walls, run the odds, accept the number, and fly. And underneath all of it sits an assumption that most people never question. The assumption is that this fog stays roughly the same, that the amount of junk up there is a fixed background, like weather, that we deal with year after year. One scientist did the math on that assumption in the 1970s and found something that made his colleagues furious. He showed that the fog makes more fog, that the debris up there behaves like a population, and populations grow. He predicted a chain reaction with no off switch. In 1978, a scientist at NASA published a paper that nobody wanted to read, and it described a future where the sky closes. His argument ran like this: every object in orbit is a target, every object in orbit is also ammunition. When 2 of them meet, they do not just die, they multiply. A single collision between 2 dead satellites produces thousands of pieces of wreckage, and every one of those thousands is now its own object, on its own orbit, crossing paths with everything else, capable of causing the next collision, which produces thousands more. Follow the logic and you reach a threshold. Past a certain density of junk, the collisions start generating new debris faster than the atmosphere can drag the old debris down. At that point, the population climbs on its own. You could stop launching entirely, freeze the space industry forever, ground every rocket on Earth, and the number of objects up there would keep rising. For decades, this was a theory in a journal. Then reality started running the experiment. In 2007, a country tested a weapon on one of its own weather satellites, hitting it head-on and shattering it deliberately. That single act produced more than 3,000 trackable fragments, plus vastly more too small to track. Much of it went into a high orbit where the air is so thin that fragments will stay for centuries. Every satellite that flies through that altitude now, and every satellite that flies through it in the year 2200, is dodging the pieces of one afternoon. 2 years later, it happened by accident. An active communications satellite and a dead military satellite collided over Siberia at roughly 26,000 miles an hour. Nobody planned it. Nobody saw it coming in time. 2 intact spacecraft turned into roughly 2,000 trackable fragments, and an estimated cloud of far smaller pieces that no one will ever count. Those two events alone added an enormous slice of everything we currently track. That is the mechanism running live in front of us. Here is the part that ties back to everything you have heard so far. The debris we can track is a nuisance. We dodge it. The debris we cannot track is the killer, and every collision manufactures that stuff in astronomical quantities. Each smash pours millions of new invisible fragments into the fog. So the danger arrives quietly, in the years afterward, as a slow thickening of the invisible haze that eats windows and solar wings and mirrors, and we are pouring more hardware up there than ever. Constellations of thousands of satellites are going into low orbit right now, with tens of thousands more planned. Companies argue that low orbits clear themselves because the thin air pulls things down within a few years. That is true at low altitude. It is far less true higher up. And it does nothing about the fragments already parked in the centuries-long orbits. The worst case is a sky wrapped in a shell of shrapnel. No launches, no new telescopes, no leaving. Humanity, locked on its own planet, by its own garbage. That is the danger we made for ourselves, in the thin shell of space right above our heads. Now leave the shell behind. Because the moment a human being climbs out of a hatch, the armour drops from a foot of ceramic and metal down to a few millimetres of cloth, and it is wrapped around a body. Everything protecting a spacewalking astronaut from a vacuum is roughly as thick as a slice of bread. Look at the suit, and your brain reads armour. It is white, bulky, rigid, huge. It looks like a machine you climb inside. That impression is a lie told by insulation and by the pressure holding it puffed out like a balloon. Peel it open. There are about 14 layers in the fabric, and every one of them is thin enough to fold. Start on the outside. There is a woven fabric blended from 3 threads. One thread is the same slick material used in outdoor jackets. One is a flame-resistant fibre that refuses to burn. One is the fibre from a bulletproof vest. Underneath that sit several sheets of aluminized plastic film, shiny and crinkled, the kind of stuff that feels like a snack wrapper. Those handle the temperature, which swings from scalding sunlight to a cold that would crack steel, sometimes within the same hour. Then, near the skin, a rubber-coated bladder. That bladder holds the air. It is the only thing between a human body and nothing at all, and it is thinner than a kitchen glove. Add it all up and you get a few millimetres of cloth. Now compare that to the wall of the station the astronaut just floated out of. That wall has a bumper, a gap, ceramic blankets, layers of fabric, and a thick aluminum shell behind it. Thicker than your hand, and even that has soft spots. The suit gets a few millimetres of cloth. Why the difference? Because a suit has to bend, an elbow has to move, a knee has to fold, a finger has to curl around a tool. You cannot stuff a bumper and a 3-inch standoff gap into a glove and then ask someone to turn a bolt with it. The whole trick that saves the station is forbidden here, because the trick requires rigidity and a human being requires joints, so the fabric does what it can. It works exactly like a soft bumper. The outer weave shatters a small grain and lets the debris spread through the layers. Each sheet of film takes a little energy out of the spray. By the time anything reaches the bladder, it has been chewed up by a dozen thin sheets in a row. For specs, this works. For anything with real mass, the suit is a shirt. The astronauts know. Every one of them has been briefed on the numbers. Before an American spacewalk, engineers calculate the odds of a suit puncture for that specific outing based on how long it lasts, where the body will be positioned, and how much of the sky is blocked by the station's own bulk. Then somebody signs off. They go out anyway. 6 hours, sometimes 8. Hanging off a handrail 400 miles up, doing careful work with their hands, inside a garment you could tear with a pair of scissors. Nobody has ever been hit, not once, in hundreds of spacewalks over decades. That is a remarkable run, and it is worth being honest about what it is. It is a run of good luck stacked on top of good engineering, and the luck is doing more of the work than anyone likes to say. Here is the twist nobody expects. Dust has already hurt astronauts on spacewalks. It has drawn blood, ended an outing early, and forced a crew back inside. It just did it in a way that no engineer saw coming. In 2007, an astronaut working outside the station stopped, looked at his left glove, and saw a hole in it. He was partway through a spacewalk, moving hand over hand along the outside of the structure, the way every spacewalker travels. There are handrails everywhere out there. Long metal bars bolted along the modules designed to be grabbed. They are the sidewalk of low Earth orbit. He found a tear in the thumb area of his glove. A gouge, deep enough to eat clean through the outer protective layer. The spacewalk was ended early. He came back inside, and the investigation that followed found something that changed how every spacewalk since has been planned. The handrails had turned into blades. Think about what has been landing on those bars every day for years. Specks, grains, flecks of paint. Each one hits the aluminum and blows a tiny crater in it, and around the rim of that crater the metal freezes into a raised lip. Sharp, jagged. A microscopic burr standing up out of a smooth surface. Multiply by years of exposure. Every handrail on that station is slowly growing a coat of tiny knives, machined by dust, one grain at a time. So the astronaut's glove was cut by the station itself. The suit fabric can shrug off a grain arriving at 40,000 miles an hour, and then a slow, deliberate human hand closes around a rail and the fabric loses. 20,000 times slower, vastly more dangerous. The response was immediate and thorough. Crews now inspect their gloves during spacewalks, several times on a schedule. They photograph the palms and fingers and send the images down for engineers to study. They carry patch kits. Sharp edges get covered. Some crews have flown up with wraps to cover the worst rails. Engineers now track which stretches of handrail have taken the most punishment over the years and route spacewalkers around the bad ones. New glove designs added tougher layers exactly where the wear shows up. Now go back to the direct threat, the one everybody worries about first. Say a grain gets through the fabric. What happens to the human? The suit runs at about 4 pounds of pressure, roughly a third of the air pressure at sea level, filled with pure oxygen. A hole a millimetre or two across leaks slowly, and the backpack can pump oxygen in faster than the hole lets it out. That buys time. The astronaut feels a hiss they probably cannot hear, sees a warning light, and starts moving for the airlock. Anything bigger, and the arithmetic collapses. The suit empties. Consciousness goes in about 15 seconds, and the strike would arrive in total silence. Vacuum carries no sound. There is no warning, no whistle, no crack. There would be an alarm and a light and a very long float back to the hatch. That is the reality 400 miles above the ground, with a rescue crew 20 feet away and a hatch you can reach in 3 minutes. Now take that same fabric, that same body, that same silence, and put it somewhere with no hatch, no station, no rescue. Somewhere that has been taking this bombardment at full strength, with nothing to soften it, for 4.5 billion years. We have been there. We walked around on it, and it chewed our suits to pieces. Earth has an atmosphere, and that atmosphere is 100 miles of armour. Every grain of dust that comes at this planet hits that air and stops. It heats, it glows, it dies at an altitude of about 60 miles. You call the result a shooting star and make a wish on the death of a sand crystal. The moon has nothing. No air, no shield, no burn-up altitude. Every grain that arrives at the moon lands, at full speed, onto solid rock, forever. The result is a surface that has been ground into powder. The grey dust covering the moon, the stuff Apollo boots kicked up, is pulverised rock, ground out by 4.5 billion years of continuous impact. Scientists call the process gardening, which sounds gentle, and means that the top layer of the entire moon gets turned over and over like earth under a spade by explosions endlessly. A spacecraft mapped the moon before and after, comparing photographs of the same ground taken years apart. It found hundreds of fresh craters that had appeared during the mission itself. It also found something stranger. Thousands of faint splotches scattered across the surface, places where the ground had been disturbed by the spray thrown out from nearby strikes. The churn is running far faster than anyone estimated. The top inch of the moon gets completely reworked in a blink of geological time. Another spacecraft went looking for something even weirder, and found it. The moon is wearing a permanent cloud of dust. Grains get knocked off the surface by incoming hits, arc up for a while and fall back. The cloud never settles because the bombardment never stops, and when the moon passes through a comet's debris trail, the cloud gets visibly thicker. The moon has weather. The weather is made of shrapnel. Now the part that ended carriers before it ended equipment, the dust itself is a weapon. Every grain of it was made by a violent impact and then left alone. There is no wind to round it off, no water to smooth it, no chemistry to weather it, so the particles stay jagged. Some are tiny glass shards, some are barbed like fish hooks. The Apollo crews found out fast. It stuck to everything. It ground into the joints of their suits and made them stiff. It scoured the visors. On the last landing, one crew found the outer layer of a boot worn through after only 3 walks, and the wear on the suits was severe enough that a longer stay would have destroyed them. The dust got into the cabin, into their lungs, into their eyes. One astronaut developed what he described as hay fever from it. 3 days on the surface, and the moon was already eating the equipment, so a permanent base cannot sit on top of that. The plan for any serious lunar habitat involves burying it, piling several feet of loose regolith over the roof, and letting the moon's own broken bones absorb what comes. We survive by hiding under the debris of the last 4 billion years of bombardment. That is the moon, sitting quietly next door, in the calm part of the solar system. Now leave the neighbourhood. Because 1 billion miles away, a spacecraft was about to fly through the most beautiful shooting gallery ever created, and it went in holding its dish over its face. The plan was to thread a spacecraft through a gap that nobody had ever measured at 77,000 miles an hour, hoping the gap was empty. Cassini had been circling Saturn for 13 years. It was running low on fuel, and the team had a problem. A dead spacecraft drifting around Saturn could eventually crash into one of the moons, and 2 of those moons have oceans under the ice, and nobody wanted Earth bacteria landing in an alien ocean. So they chose a spectacular ending. 22 dives through the gap between Saturn's cloud tops and the innermost edge of the rings, followed by a final plunge into the planet itself. The gap is about 1,200 miles wide. That sounds enormous. It is the distance from Chicago to Miami, and the spacecraft was crossing it once a week. Nobody knew what was in there. The rings are made of ice mostly, in chunks ranging from boulders down to smoke. The gap looked clear in every image, but images cannot show you a grain of dust from 1 billion miles away. And at the speed of that crossing, a piece of ice the size of a grain of sugar carries enough punch to end the mission instantly. So the engineers did something wonderfully crude. Cassini has a radio dish about 13 feet across, a solid parabola of metal, the thing it uses to talk to Earth. They turned it forward and hid behind it. For the first dive, the spacecraft flew through the gap with its dish pointed into the wind like a knight raising a shield, with the delicate instruments tucked in the shadow behind it. Talking to Earth was impossible in that position, so the team lost contact on purpose for hours while their spacecraft crossed the unknown. Then they waited. The signal came back, and the science team started laughing, because the data made no sense. There was almost nothing in there. They had expected a rattle of hits. They got near silence. A handful of specks, smoke-sized, barely anything. The team started calling the gap the Big Empty, and they were openly confused. The region between a giant planet and the most famous ring system in the universe turned out to be one of the cleanest places any spacecraft has ever visited. Nature had swept the corridor clean, and nobody had predicted it. The engineers grew bolder. For later dives, they stopped hiding behind the dish and let the instruments look around. The spacecraft went in naked 21 more times, and every pass came back with new science, because the shield had been blocking the view of the very thing they came to study. The last dive went into the atmosphere. Cassini burned up on purpose, transmitting to the final second. But look at what that mission proved by accident. Grains of dust are so dangerous that a team of the best engineers alive threw away their radio link, blinded their instruments, and flew a $2 billion spacecraft through the dark behind a metal plate on the chance that a speck of ice might be waiting. They were fighting something they could not see. Which raises a beautiful question. If dust is invisible and untrackable and lethal, how does anyone measure it at all? The answer is that someone realized the impacts themselves could be turned into an instrument. You stop trying to avoid the grains, you start listening to them die. Every time a grain of dust vaporizes on a spacecraft, it screams. The trick was noticing. Remember what the impact makes. A puff of plasma born in a millionth of a second made of charged particles, and charged particles moving around produce an electrical signal. Now remember what a lot of spacecraft carry. Long thin antennas sticking out like whiskers, built to measure the faint electric fields of space. Those antennas were designed to study the solar wind and the invisible waves rippling through it. Somebody realized those antennas were also hearing something else. Every so often, the data showed a sharp spike, a crack, an impulse lasting a few thousandths of a second. It was noise. It was garbage. It was ruining the measurements. It was dust. The plasma flash from each impact jolts the electrical potential around the spacecraft, and the antenna picks it up as a pop. Convert those signals to sound, and you can hear it. A rain of clicks and crackles, like a bad radio, like a fire, like hail on a tin roof. There is a quirk in the signal that makes this work beautifully. The amount of electric charge released by an impact climbs with the speed of the grain raised to almost the fourth power. Double the speed, and the pop gets more than 10 times louder. So these accidental detectors are nearly deaf to slow dust, and exquisitely sensitive to the fast grains, which are the only ones that can hurt you. Suddenly every spacecraft with an electric field antenna became a dust detector, including ones launched before anyone thought of the idea. Missions from the 1970s have been re-examined, and their static reinterpreted, and the noise turned into a map. The Voyagers crossed the ring plane of the outer planets, and their instruments erupted with thousands of hits, a burst of frantic clicking as they punched through sheets of debris nobody could see. Those recordings still exist. They are the sound of a machine being sandblasted 1 billion miles from home. Then somebody built a detector on purpose and handed the job to college students. The dust counter on the spacecraft that flew past Pluto was designed, built, and operated by students at a university in Colorado, undergraduates. It is a thin plastic film that registers a signal every time a grain smacks it. Small, cheap, simple. It has now flown farther than any dust detector in history, and it is still working. And it came back with a result nobody wanted. Out past Pluto, way beyond the orbit of Neptune, the dust count stayed high, higher than the models predicted. The far edge of the solar system should be thinning out into nothing, and instead the student's little plastic sheet kept registering hits. The simplest explanation is that the Kuiper belt reaches much farther than we believed, and that there is a great deal more out there grinding itself into powder than anyone had drawn on the map. An undergraduate class project quietly redrew the edge of the solar system, so we can hear dust, we can count it, we can map it. None of that tells you what it is made of. To answer that, you need to catch a grain travelling at 14,000 miles an hour and bring it home intact without letting it vaporize, which sounds impossible until somebody invented a solid made almost entirely of air. The material looks like a piece of sky someone cut out with a knife. It is a solid. You can hold it. It is faintly blue, like a shadow on snow, and it glows at the edges. It weighs almost nothing because it is roughly 99.8% empty space. It is made of silica, spun into a web of threads a few atoms thick with air filling everything between. People call it frozen smoke. It is one of the lightest solids ever made. Somebody looked at that and saw a butterfly net. The problem with catching dust is the problem in this whole story. Speed. Any grain you want to catch is arriving fast enough to destroy itself on contact, and whatever you catch it with. Stop it suddenly and it vaporizes, and you have caught a puff of gas that used to be a scientific sample. The fix is to stop it gradually. Give the grain a very long distance to decelerate and it survives. Frozen smoke does exactly that. A grain enters and starts pushing through a web so flimsy that it barely resists, and then it pushes through more of it, and more, for thousands of times its own length. It slows down over inches instead of a millionth of an inch. It burrows to a stop, warm, dented, and alive. They flew trays of the stuff to a comet. The spacecraft opened its collector like a tennis racket, flew through the comet's dust halo at about 14,000 miles an hour, closed the racket, and came home. The capsule slammed into Earth's atmosphere over the desert, faster than any human-made object had ever re-entered, and parachuted down onto salt flats in Utah. Inside the trays were tracks, thin carrot-shaped tunnels, each one with a grain of comet sitting at the bottom of it. Then the results came in, and they broke the textbook. Comets form far out, in permanent deep freeze, at the cold edge of everything. So the grains should have been cold chemistry all the way down. Instead, the trays held minerals that only form in searing heat, crystals that must have been cooked close to the sun. which means material from the hottest part of the young solar system somehow travelled all the way to the coldest part and got frozen into a comet. The early solar system was mixing itself like a stirred pot, flinging matter across billions of miles, and nobody knew. They also found a simple amino acid in the samples, one of the building blocks that living things use riding on a comet. Then they did something clever with the leftovers. The collector had a second side exposed to catch grains from between the stars. Finding those tracks meant scanning millions of microscope images, so they put the images on the internet and asked the public to help. Thousands of volunteers went looking. Ordinary people, on home computers, found a handful of tracks that appear to be genuine interstellar dust. Specks from outside the solar system sitting in a lab because a stranger clicked on a fuzzy picture. We have samples of another star's neighbourhood. Grand total, a few grains. And that gentle capture, at 14,000 miles an hour, is the friendly version. Because another spacecraft had already flown at a comet 10 times faster than that, straight into the jets, on purpose, with a shield on the front and no way to slow down. In 1986, Europe threw a spacecraft at the most famous comet in history at 150,000 miles an hour and told it to take pictures on the way past. The comet only comes by every 76 years. Everybody alive gets one shot. So the plan was aggressive to the point of rude. Fly straight at the nucleus, get within 400 miles, and photograph the thing nobody had ever seen. The engineers knew what that meant. At that speed, the comet's dust halo is a shotgun blast held at point-blank range. They built a shield on the front of the spacecraft. Thin aluminum sheet in front, a gap behind it, and a slab of the bulletproof fibre at the back about half an inch thick. The same trick from decades earlier aimed at a comet. On paper, it could survive a grain weighing a full gram, arriving 50 times faster than a bullet. The spacecraft spun as it flew like a rifled bullet, holding the shield steady toward the target. It went in. The camera started sending pictures. Fuzzy at first, then better, then astonishing. A dark, lumpy, potato-shaped mountain of ice, blacker than coal, with jets of dust firing off its sunlit side. The first human look at the heart of a comet, arriving live. The dust hits began. The team could see them in the data. The count rose, then it climbed. The spacecraft ploughed into a jet. 14 seconds before closest approach, something big hit it. Estimates put that grain at somewhere between 1 and 2/10 of a gram, the weight of a few grains of rice. It struck hard enough to kick the entire spacecraft off its spin axis by nearly a degree, and the machine began to wobble like a dying top. The dish swung off Earth. The signal collapsed. Down in the control room in Germany, the room where every scientist in Europe had gathered for the night of the comet, the data stopped. For 32 minutes they got fragments. The signal came back as the wobble happened to swing the antenna past Earth, then vanished again as it swung away. Pieces of a heartbeat. Nobody knew if there was still a spacecraft out there or a cloud of debris pretending to be one. On board, automatic dampers were fighting the wobble and slowly winning. It came back. Battered, tumbling less, still transmitting. The damage list was long. The camera was destroyed. It died after taking its pictures, which is the closest thing to a heroic death a machine can have. Other instruments were shredded. The shield's front sheet had been beaten to pieces, and now the important number. The shield was rated for 1 gram. The grain that nearly ended the mission weighed about 1/7 of that. 1/10 of a gram. On a spacecraft designed and tested to take 10 times more, nearly killed it anyway. The strike only had to shove. The spacecraft survived, and it later flew past a second comet, half blind, and did more science. Now, hold that image. A shielded, spinning, armoured probe staggered by a crumb, and then picture the opposite kind of spacecraft. One with no shield at all, made of a sheet thinner than a soap bubble, hundreds of feet wide, flying with everything exposed. There is a spacecraft design that has no hull, no shield, and no protection of any kind, and it is the one that might carry us to another star. A solar sail catches light. Sunlight carries no weight, but it carries momentum, and momentum bounced off a mirror gives a push. the push is absurdly gentle. On a sail the size of a tennis court, sunlight presses with about the force of a paperclip resting on your palm. Push forever, though, and gentle winds. A sail needs no fuel. It just keeps accelerating day after day, year after year, and eventually it is moving faster than anything a chemical rocket could throw. The catch is that this only works if the sail is impossibly light, so they build them out of almost nothing. Japan flew the first true one, a square about 46 feet on a side, made of plastic film a few millionths of an inch thick, roughly a tenth the thickness of a human hair. You could crumple the entire spacecraft into your fist. A crowd-funded sail from a space society flew later, unfolding from a package the size of a loaf of bread. An American mission unfurled a sail the size of a small apartment from a spacecraft you could carry under one arm. Now look at that from the dust point of view. A sail is a target thousands of times bigger than a normal spacecraft, made of film you could tear with a fingernail, held open to the sky, with no armour and no possibility of armour. Adding a bumper would add mass, and mass is the one thing a sail cannot have. The defence is forbidden by the physics of the mission, so every grain goes straight through, every single one. Then comes the surprise. It barely matters. A sail with a hole in it is still a sail. Light bounces off the parts that remain. Punch 1,000 holes in it, and you lose the light that would have hit those holes, which is a fraction of a percent. The most defenceless structure ever flown turns out to be the most forgiving, because it has nothing inside it to break. There are no circuits to fry, no air to leak, no crew to kill. There is only surface. The danger is tearing. A hole in a stretched film wants to become a rip, and a rip wants to run. So engineers weave a grid of stronger threads across the sail, the same trick used in tents and kites, so a tier stops when it reaches a line. Sunlight is the weak version of this idea. The serious proposal is to skip the sun and use a laser. Build a bank of lasers on Earth, aim them at a sail the size of a room with a chip the weight of a paperclip riding on it, and fire for a few minutes. A few minutes of that gets you to 1/5 the speed of light, 20 years to the nearest star instead of 80,000, and the moment you reach that speed, every rule in this story inverts. Dust stops being erosion and starts being artillery. Before we go out there, though, there is a spacecraft flying right now that has already tasted a fraction of it. It is the fastest thing humans have ever built, and it is being sandblasted every 12 seconds. At its closest approach to the Sun, the Parker Solar Probe moves at about 430,000 miles an hour. Take a second with that. New York to Los Angeles in 20 seconds, around the Earth in under 4 minutes. It is the fastest object human beings have ever made by an enormous margin, and it earns that speed by falling toward the Sun and whipping around it. It is flying into the thickest dust in the solar system while doing it. The inner solar system is dirty. Close to the Sun, the dust piles up, and the probe dives right through the densest part of the pile, over and over, on a loop. The numbers from those dives are stunning. On one orbit, there were stretches where the spacecraft was struck by a hypervelocity grain every 12 seconds. Every 12 seconds, for hours on end. Across the mission, it has been hit tens of thousands of times. The grains are absurdly small. Most are between 2 and 20 microns across. A human hair is about 100 microns thick. So the typical attacker is a fraction of the width of a hair, and there are so many of them that the spacecraft is essentially flying through a mist. Each one arrives, vaporizes, ionizes, and detonates into a puff of plasma that lasts less than 1,000th of a second. Thousands of tiny explosions popping across the skin of the machine all day, every pass. Then the interesting part. Some hits are big enough to knock loose actual pieces of the spacecraft itself. Chunks of coating and insulation get blasted off and drift alongside, because in the vacuum they have nowhere to go. And they are travelling at the same absurd speed as the ship they came from. So they hang there, and they float in front of the cameras. Debris shed by dust impacts has drifted through the field of view of the navigation cameras, catching sunlight, throwing streaks across images and confusing sensors designed to find stars. A spacecraft, blinded temporarily by its own paint, kicked loose by grains it never saw. Some of those debris clouds linger near the spacecraft for up to a minute, buzzing with electrical charge, disturbing the very instruments trying to measure the sun. The front of the machine carries a shield of carbon foam pressed between carbon plates, about 4.5 inches thick, facing temperatures near 2,500 degrees. That shield is also the surface collecting most of the grit. It is being cooked and sandblasted at the same time on every single pass. The spacecraft is dissolving. Slowly, invisibly, one microscopic explosion at a time, and it is broadcasting the whole thing home. Because the team realized these impacts were data, they now use the dust hits to map the dust. And here is the point that matters for everything coming next. 400,000 miles an hour sounds like a Starship number. It is 1/5 of 1% of the speed of light. It is nowhere close, and already the machine is being visibly eaten. That mist the probe is flying through has a name and a shape. It is a vast, flattened disk of ash that fills the entire inner solar system, and you have almost certainly seen it with your own eyes, without knowing what you were looking at. Go somewhere with no city lights a couple of hours before sunrise and look east. If the sky is dark enough, you will see a faint triangle of light leaning up from the horizon. It looks like dawn arriving early. Old astronomers called it the false dawn. It is soft, cone-shaped, and easy to mistake for a distant town. There is no town. You're looking at sunlight reflecting off 1 trillion grains of dust, spread through the entire inner solar system in a flattened disk, and you're sitting inside it. The zodiacal cloud. It is the biggest structure in the solar system that anybody can see with their bare eyes, and almost nobody knows it is there. The grains are ash. Most of them come from comets. Every time one of those ice mountains swings past the sun, it sheds. Some fall apart entirely. The debris stays in orbit, spreads out, flattens into the plane where the planets live, and joins the cloud. A smaller share comes from asteroids grinding each other down in collisions. So the cloud is the accumulated remains of everything the solar system has destroyed. It is a graveyard, lit up, arranged in a disk. Now the elegant part. That cloud should not exist, because it is constantly draining away. Sunlight does something sneaky to a small grain. The grain absorbs light coming from the sun, then radiates that heat back out in all directions. Because the grain is moving in its orbit, the outgoing radiation carries away slightly more momentum from the forward side. It acts like a headwind. The grain feels a permanent tiny drag. Drag means the orbit shrinks. So every grain in the zodiacal cloud is spiraling inward toward the sun, slowly, and will eventually fall in and be destroyed. The whole cloud is draining into the fire. The drain is fast in cosmic terms, tens of thousands of years for the small stuff. The cloud you can see this morning should have emptied itself millions of times over. It is still there, which means something is refilling it, constantly, right now. Comets are dying and asteroids are colliding at exactly the rate needed to keep that ghostly triangle in the sky. The cloud is a fountain. What you see is the spray. There is one more piece of the cloud you can see, and it hides in the opposite corner of the sky. Look directly away from the sun near midnight, and there is a faint oval smudge called the counterglow. It appears because the grains out behind us bounce light straight back toward the source, the way a road sign catches headlights. Astronomers use that smudge to prove the cloud wraps all the way around us. Some of it lands here. Roughly 5,000 tons of space dust settles onto Earth every year. It falls silently, all over everything, all the time. It is on your roof. People with magnets and microscopes have pulled genuine micrometeorites out of the gunk in city gutters, grains that formed before the planets sitting in a downspout. Now follow that draining cloud inward. Follow it all the way down toward the sun, where every grain eventually goes. Somewhere near the bottom, the sun stops accepting deliveries and starts destroying them before they arrive. There should be a boundary, a place where dust simply ends. Astronomers predicted it almost a century ago, and then spent 90 years unable to see it. In 1929, an astronomer argued that there must be a region around the sun where dust cannot exist, and then the idea sat there, unproven, for the next 90 years. The logic is simple. A grain of dust spiraling toward the sun gets hotter the closer it goes. Eventually it gets hot enough to stop being a solid. It sublimates, turning straight from rock into vapour, and the vapour gets stripped apart and swept away by the solar wind. So there should be a dust-free zone, a clean bubble around the sun swept by heat, where nothing solid survives. Nobody could see it. To look at that region, you would have to stare directly into the brightest object in the sky and pick out a faint glow right next to it. From Earth, it is hopeless. The sun's glare drowns everything. The only way to see it was to go there. The solar probe carries a camera that looks sideways, out at the space around the spacecraft rather than at the sun. As the probe dove closer than anything had gone before, that camera watched the brightness of the dust cloud, and the glow started to fade. Beginning around 19 solar radii out, roughly 7 million miles from the surface, the dust visibly thins. The cloud starts giving up. The analysis suggests the truly empty zone begins somewhere inside about 5 solar radii, a couple of million miles from the fire. There is a hole in the middle of the solar system, a clean spot millions of miles wide wrapped around the sun like a bald patch, where 100 trillion tons of ash simply cease to be. An idea from 1929 confirmed by a spacecraft that had to nearly touch the sun to check. The boundary is blurry, and the reason is chemistry. Different grains die at different distances. Icy material goes first, far out. Ordinary rock holds on until it reaches somewhere around 2000 degrees. Carbon is the toughest of all, and it survives closest to the fire. So the inner edge of the cloud works like a ladder rather than a wall. Grains drop out one kind at a time as they spiral in, and the haze thins in stages. There is a way to see the outer part of this with your own eyes. During a total eclipse, the pearly halo around the black disk of the moon is partly dust, glowing at its very brightest, right at the lip of the hole. Sit with the strangeness of it. The most dangerous place in the solar system to fly is also, at its very centre, the cleanest. The sun defends a small territory around itself by vaporizing everything that comes near, and the reward for surviving that heat is a region with nothing left to hit you. That is the dust map of home, a thin haze near Earth, a thickening mist as you fall inward, a swept, clean bubble at the bottom, a slow drizzle of ash filling it all from above. Now leave, fly out past the planets, past the Kuiper Belt, past the last place the sun's wind reaches, and into the dark between the stars. Everybody assumes it is empty out there. The word people use is void. It is filled with smoke, and the smoke is what stands between us and everything else. Interstellar space contains, on average, about 1 atom per cubic centimetre. That is a vacuum better than anything we can make in a laboratory on Earth, and roughly 1% of the mass out there is dust. Do the arithmetic on what that means, because the number is almost funny. Interstellar grains are around 1/10 of a micron across, 1,000th the width of a hair. Work out how many fit in a given volume, and you get roughly 1 grain of dust in every 500,000 cubic meters of space. That is 1 speck of soot floating somewhere inside a volume the size of a large office block. 1 grain in a cube 80 yards on a side. The emptiest thing you have ever imagined. We know what the grains are made of because they leave fingerprints on starlight. Light passing through a dust cloud comes out dimmed and reddened, and the exact pattern of the dimming tells you what absorbed it. Silicate rock, similar to sand. Carbon, in various forms, essentially soot. Out in the cold, dense clouds, the grains grow coats of ice. So the stuff between the stars is smoke and grit and frost. The same material that eventually clumps into planets. You are made of it. Every atom heavier than hydrogen in your body spent time as interstellar dust before the sun formed. We have even caught some. In the 1990s, 2 spacecraft in the outer solar system detected a steady stream of dust blowing through from outside, riding in from the local cloud we're currently drifting through. And the collector that went to a comet also caught a handful of interstellar grains, later found by volunteers scanning pictures at home. Now here is where the emptiness stops helping you. 1 grain per office block is nothing when you sit still. Fly through it, and you sweep a column. Cross 4 light years and that pencil-thin column adds up. A sail crossing to the nearest star will run into a very large number of grains, because it is sampling a volume you cannot picture. and we happen to live in an unusually clean patch. The Sun sits inside a cavity called the local bubble, a region blown clear by exploding stars millions of years ago. The density around here is well below the galactic average. Elsewhere in the galaxy, dust piles up into clouds thousands of times thicker. There are lanes across the Milky Way so full of grit that they blot out the stars behind them completely. You have seen them in photographs. Those black rivers cutting across the bright band of the galaxy are dust, blocking the light of 100 billion suns. Fly through one of those at speed and nothing you build survives. That same dust hides the heart of our own galaxy. Invisible light, the centre of the Milky Way is completely invisible from Earth, buried behind so much grit that astronomers had to build infrared telescopes just to peek through it. So the picture is set, a whisper of smoke spread across an unimaginable emptiness sitting quietly in the dark. Now take a speck of that smoke, hold it perfectly still, and drive a spacecraft into it at 1/5 the speed of light. The arithmetic that comes out of that collision is the reason this entire story exists. Take a grain of interstellar dust 1/10 of a millimetre across. It weighs about 1/1000th of a gram. You could not see it, feel it, or find it if you dropped it. Hit it at 1/5 of the speed of light and it delivers about 2 million joules. That is the energy of roughly half a kilo of high explosive. 2 hand grenades going off at a single point on your spacecraft from one speck of soot. Compare it to the chip in that station window. Same grain, arriving at orbital speed, carries 36 million times less energy. The exact same piece of dust. One version scars a pane of glass, the other version is a bomb. That is what the square in the energy equation does when you push the speed into the region where light lives. The dust stays exactly the same spec it always was. You do all the work and the dust collects the bill. Now the honest part. Grains that big are rare out there. The typical interstellar speck is 1,000 times smaller, closer to 1/10 of a micron, and it lands like a firecracker rather than a grenade. A sail will meet billions of the small ones and only a scattering of the monsters. The mission lives or dies on that ratio, and nobody has measured it well enough to promise anything. Now put that against the design of the ship. The plan for the nearest star involves a sail the size of a room, carrying a chip the weight of a paperclip, pushed to 1/5 light speed by a bank of lasers. The whole spacecraft weighs a few grams. It has to because the lasers can only push so hard, and mass is the enemy. A few grams. Facing 2 hand grenades per spec. Scientists ran the numbers properly. Their conclusion is grim and specific. Over the crossing to the nearest star, dust bombardment erodes something like 0.5 millimetre off the leading surface. Each grain arrives, dumps its energy into a tiny volume in an instant, and the surface material explodes outward. Explosive evaporation. The leading edge boils away, one microscopic detonation at a time for 20 years. 0.5 millimetre sounds like nothing. Hold that thought against the actual hardware. The sail is a few hundred atoms thick. The chip is a wafer. 0.5 millimetre of erosion swallows that entire spacecraft several times over. There is one saving grace, and it is the shape of the thing. A sail is a flat sheet. Turn it edge onto the direction of travel after the lasers shut off, and it presents almost no area to the oncoming dust. Fold it, roll it, hide the chip behind the smallest possible cross-section, and you shrink the target from the size of a room to the size of a needle. The engineers who proposed the mission worked this out. Their ship is designed to fly like a dart, not a parachute. Everything about the geometry is chosen to give the dust the smallest thing to hit. That handles the dust. It does nothing at all about the gas, and the gas is the part that turns the whole idea inside out. Because at 1/5 the speed of light, empty space stops behaving like emptiness. Ordinary hydrogen, the loneliest and most harmless atom in the universe, stops being a gas. It becomes a beam. There is 1 atom per cubic centimetre out there, and at relativistic speed, that thin nothing becomes a weapon. Sit in the spacecraft's frame of reference and the universe looks different. From the ship is standing still and the entire galaxy is charging at it at 1/5 the speed of light. Every hydrogen atom in the way is now an incoming particle carrying millions of electron volts of energy. Physicists build machines to do this. Particle accelerators cost billions of dollars and take up whole valleys, and what they produce is a beam of atoms at high energy aimed at a target. The Starship builds one for free by moving. It flies into the beam it is creating. Now watch what that does to solid matter. The hydrogen arrives and buries itself. Each atom drives a fraction of a millimetre into the material and stops there, wedged between the atoms of the hull. Helium does the same, at about the same depth. so the two pile up together in the same thin layer, and they cannot get out. Gas atoms trapped inside a solid are slow, stubborn things. They wander around and find each other. They collect. They form bubbles. The bubbles grow, packed with pressurized gas sitting just under the surface. Then the surface starts to lift. Engineers call this blistering. The skin of the material swells into domes, like paint on a hot radiator, and eventually the domes rupture. The blister bursts, throws off a flake, and exposes fresh material underneath, which starts collecting gas immediately. The next layer blisters. The next flake goes. The ship peels itself from the inside out, all the way to the target star. We know this happens because we have seen it. The exact same process wrecks the inner walls of experimental fusion reactors, where hydrogen and helium slam into the lining. There is a whole field of study devoted to it. Nobody had to guess what a relativistic ship would suffer because the answer was already sitting in a laboratory, blistering. The heavier atoms make it worse in a different way. Carbon, oxygen, iron, arriving with that much energy, punch tunnels through the material and leave a permanent track of wrecked structure behind them. Studies of the crossing estimate about 1/10 of a millimetre of that kind of damaging quartz over the journey. Graphite handles it better, which is one reason the proposals keep coming back to carbon. None of this can be switched off. The damage comes from the ship's own speed, and the only cure is to slow down, add it up. The erosion from the trip runs at roughly a millimetre of material per 4 light years travelled. For a large starship, a millimetre is a shrug. Fly 4,000 light years and you lose a metre of skin, and any serious ship would carry that. For a gram-scale sail, a millimetre is everything it has several times over. So the smallest possible ship, the only kind we know how to accelerate, is exactly the kind the dust and gas destroy. That is the trap. The mission is possible because the ship is light, and the ship dies because it is light, unless somebody finds a way to fight back. And the ideas on the table range from clever to completely insane. You cannot dodge, you cannot brake, and you cannot armour up because armour is mass, and mass is the thing that makes the mission impossible. So the people who want to reach another star have gotten creative. The first idea is shape. Make the ship a needle. Everything about the geometry exists to shrink the front. Nothing wide, nothing flat, nothing facing forward. A spacecraft built like a dart presents a target smaller than a grain of rice for the entire journey, and the dust mostly streams past on either side. Every proposal starts here because it costs nothing. The second idea is chemistry. Some materials survive this better than others. Quartz gets chewed up. Graphite shrugs. So the leading edge gets built out of carbon, and the sensitive electronics hide behind it. The third idea is sacrifice. Coat the front in a layer whose job is to be eaten. It boils away for 20 years, and it is thick enough to last exactly as long as the journey and no longer. Everything behind it arrives intact. The ship spends the crossing shedding its own skin on purpose. The fourth idea is the one that stops the room. Send a foil ahead. Fly a thin sheet of material a short distance in front of the spacecraft. Unattached, just cruising there. Any dust grain in the path hits the foil first, at full relative speed, and detonates. The grain becomes a spreading cloud of plasma. By the time the ship arrives, moments later, the cloud has expanded into a thin puff of vapour that does nothing. That is the bumper. The same idea from 1946 launched into deep space and asked to work at 1/5 of the speed of light. An engineer proposed exactly this for the star mission, and the physics holds up. The problems are engineering, making the foil hold formation, keeping it in front, building it out of the mass you do not have. Then there is the strategy that gives up on protection entirely. Send 1,000. The whole point of a gram-scale spacecraft is that it is cheap, so build a fleet. Fire 100, or 1,000, or 10,000 at the same star, spread out over years. Let the dust have most of them. If even a handful survive the crossing and phone home, the mission worked. That is a different philosophy of spaceflight than anything we have ever done. Every probe we have ever launched was precious, unique, and irreplaceable. This plan treats spacecraft the way a dandelion treats seeds, and the last idea is simply choosing the road. The dust out there is uneven. There are clean corridors and filthy ones. Map the local cloud well enough and you might thread a path through the thinnest material, the way a sailor picks a route around a storm. All of it works more or less for a tiny sail crossing 4 light years at 1/5 of light speed. Now ask the real question. the one that decides whether the galaxy is open to us or closed. What happens if we want to go faster? What happens if we want to send something big? What happens if we want to send people? Run those numbers and the answer changes completely. Here is the verdict, and it depends entirely on how greedy you are. At 1/5 of the speed of light, a gram of spacecraft can survive 4 light years. It arrives eroded, blistered, pitted, and half-eaten, and it arrives. 20 years, a needle-shaped dart, a carbon face, a sacrificial coat, and a lot of luck. The nearest star is reachable. That is a real answer, and it is worth celebrating. Now push harder, because of course we will want to. Take the same speck of dust, 1/10 of a millimeter, the one that delivered 2 hand grenades at 1/5 of light speed. Take it to 9/10 of the speed of light. That speck now arrives with the force of about 60 pounds of high explosive. 1 grain, 60 pounds of TNT. Keep going. Push to 99%, the speed you need to cross real galactic distances in a human lifetime, and the same invisible fleck lands like a 1/4 ton of explosive. There is no material that survives that. There is no shape, no coating, no clever foil. At those speeds, you're flying a spacecraft into a minefield where every grain of soot in the galaxy is a bomb, and the galaxy contains an unimaginable number of grains of soot. Now, scale it up. A crude starship is enormous. It has a huge front, which means it sweeps a huge column, which means it collects everything in a cylinder light years long. It also travels for decades or centuries, which multiplies every exposure. Bigger ships have more to hit and more time to be hit in. And the route matters more than anything. We live in a cleared space, a bubble blown open by supernovae before our species existed. Head in the wrong direction, and you fly into a dust lane, and the density climbs by a factor of thousands. Those dark rivers you see cutting across the Milky Way in photographs are walls. Any ship crossing one at relativistic speed dies inside it. So the galaxy behaves like an ocean with shipping lanes, shallows, and reefs. There are places you can go fast and places where speed is suicide, and we happen to be parked in one of the good spots. That reframes the whole dream. Every science fiction story you've ever seen assumes the hard part is the engine. Build the drive and the stars are yours. The engine was always the easy half. The road is what stops you. The universe protects its distances with something you cannot see, cannot dodge, cannot track, and cannot armour against. Something with no strength, no plan, and no mass worth mentioning. A whisper of soot, 1,000th the width of a hair sitting perfectly still in the dark for 1 billion years, waiting. Everything in this story has been the same fact told louder. A fleck of paint chips a window, a grain scars a mirror, a crumb staggers a probe at a comet, a speck of soot ends a starship. We can build the drive, we are getting close. The dust has been waiting out there the entire time. The dust never changes. We do. And the moment we go fast enough to reach the stars is the exact moment the emptiness between them stops being empty.